Good morning, good afternoon, and good evening, depending on where in the world you're joining us from. I'm Brian Mink, co-founder and president of Data Science Connect, and welcome to our expert panel, Scaling AI Beyond Vectors, Building Smarter, Faster Systems for RAG, brought to you by our friends at Vespa AI. Today, we're excited to welcome hundreds of attendees from all over the world to discuss how to build AI systems at scale for both performance and retrieval-augmented generation, or RAG. Generative AI is transforming how businesses retrieve and generate insights, but focusing on vector databases alone isn't enough to meet the demands of AI-driven application. Today, we'll learn how combining vector databases with machine learning and comprehensive search capabilities ensures relevant, actionable results and improves system performance, making your AI applications smarter and more efficient. We're honored to hear from a distinguished panel of experts today, John Bradseth, CEO and founder of Vespa AI, and Arkarsh Ramchandani, Chief Strategy Officer at Ravenpack. Before we begin, a few housekeeping items. To make this feel a little more in person, we suggest you add a photo to your profile and include your bio, LinkedIn profile, and other information you want your fellow attendees to see. Next, please take advantage of the Q&A and chat features throughout the webinar. We'll be addressing your questions throughout, so be sure to upvote the questions you'd like the panel to address. And finally, to learn more about how to leverage RAG in your AI journey, check out the call to action below throughout the webinar from our sponsor, Vespa AI. Now, without further ado, I'd like to welcome our panelists to the stage, John and Arkarsh. Welcome. Thanks for joining us today. So we'll start with some quick introductions. So why don't we start with you, John? Just tell us a little bit about yourself, what your current role is, and what you do at Vespa.
Yeah, hey guys, thanks for having me. I'm the CEO of Vespa.ai. Before that, I was the architect of that platform for the last 20 years. So pretty familiar with the technical side of what we're doing over here.
Excellent. And Arkarsh?
Thanks, Brian, for having me. Arkarsh Ramchandani, I'm the Chief Strategy Officer at Ravenpack. Before this, I've had a career on the buy side and the sell side. Most recently, I was the Director of Data Science at a hedge fund called Third Point.
Excellent. Welcome to you both. Thanks for joining us. We'll get things started just by talking a little bit about the basics. So what is RAG? What are vector databases? And how do they help enable generative AI applications? So why don't we start with you, John?
Yeah, so we all know about large language models, ChatGPT, and so on, right? If you want them to compose a poem or something, they can do that perfectly well on their own. They don't need any external information. They have learned to do all of these things from reading all the public information that's on the web, right? So that part is fine. But what if you want to use these large language models on some problem that involves up-to-date data, or more commonly maybe private data that is not on the public internet, or very detailed data? Then you actually need to supply that data to the large language model, because it won't have that data internally in the trained model, right? And that is RAG. Figure out what data that is relevant to the problem at hand, retrieving it somehow, and then giving it to the large language model as part of the prompt that you give to the model to solve some particular problem. If I can go on, vector databases sort of emerged as by accident maybe to solve this problem. At first, I think because OpenAI wanted to promote their ADA model for creating vectors from text. So the idea was to give this context to the large language model that it needed to solve some problem. You took the text you had, internal company documents or earning reports or whatever in the finance use case, and then created a vector embedding, as we call it, from each of those small chunks of text, right? So you take your text and split it into small chunks and create vectors for those. And then you can put those vectors into a vector database and retrieve the chunks by closeness to another vector. And how do you create that other vector that you compare your vectors to? You do that by having some kind of description of the data that you need to retrieve, some description of the problem that you create somehow. Maybe a user typed it, maybe the large language model comes up with it somehow, but you need some kind of description. Then you embed that in the same vector space, meaning convert it to a vector, and then you can retrieve vectors that are close to that one. and then you map those vectors back to the original text chunks, and you put those into the prompt, and voila, you have a RAG solution. So that was the general idea, right? That sort of works, right? And you're using AI both to retrieve the data and to because you're using a large language model, right? But there's no actual connection between the AI on one side and the AI on the other. So if you think about it, you can really use any kind of retrieval strategy to find the data that is most relevant to the large language model to solve the problem, right? You can look it up in a traditional relational database if that's the best way to get it, or you can use Google to search for it, or some internal traditional old school text search engine, or really whatever that can give you the information that you are needing, right? So the vector database to RAG and large language model connection is sort of tenuous and accidental, but in general, using vectors help you more relevant information in many cases, and we can get back to that.
Yeah, great overview. Akash, anything to add there?
I'll speak about it more from the product side because I think John did a fantastic introduction there about it. RAG for us, when we first, and I know we'll go into our background here, but when we first approached like the Vespa team, we didn't come to them with a vector specific problem. We thought vectorization of information is the future of, it's like the most powerful feature you can have in a complex retrieval pipeline. And, like the first time we thought of vectorization, and the story here is basically there's a lot of information that's available that's actually pretty hard to retrieve because the users don't know exactly how to encode that information. And the way we've always seen, the vectorization of text to start with, and now obviously all the multimodal types of like vectors that are coming out, but we've always seen like vectors as a way to encapsulate semantic meaning of a query. And like vectors to us was the most powerful feature that we could add in a multifaceted feature pipeline that helps you find information in a way that you couldn't really find before. And RAG for us it was probably the best tailwind we've ever received. We were working with Vespa on a search engine first. It wasn't a RAG engine, it was a search engine first. And RAG just, when we first saw ChatGPT and we saw what it could do, which is ask me a question and I'll give you an answer. That paradigm, when you take it to search, which is really what are you trying to search for? Generally speaking, you're not really looking for links to click on. You're looking for an answer. There's a class of problems where you definitely still want to look at a link, but there's a very large class of problems where you just want to get an answer. And RAG to us was that game changer in terms of thinking about now we can have something that can take and retrieve a lot of information, but not just give you links. You can always still get links. It can also provide you with a fine-tuned answer to answer your question. And that paradigm is just how we see it, that RAG could be a lot of things. One large part of it is using vectors in your RAG pipeline in order to answer questions. But the class of questions you can answer now are so much more broader than we could ever have imagined before. Like literally 4 years ago, this stuff was really hard. Now it's kind of like everybody talks about it like it's normal and everybody uses it in this context.
Yeah, those are great insights and kind of how this actually works in practice. And I think that's, one of the things that sort of comes to light when you start talking about RAG and you start talking about vectorization is just how do you scale these systems when you actually deploy them at scale? What does that really look like? And what are some of the unique factors and challenges that you have to think about when you're doing this on a really large scale and not just a small scale? So what do you guys find are some of the key factors to consider when scaling AI systems?
Yeah, I know Akash have been doing a lot of scaling over the last year, so he'll be able to speak to that as well. But I can do more of a general thing again. So there's similar to how there are AI two places in these systems typically, right? There is also two separate scaling problems. One is you have your large language model that you need to do inference in, and if you want to have a really intelligent model, it will be really big and you need lots and lots of GPUs to run it, right? So that is a scaling problem. If you actually need all that intelligence, you should outsource that scaling problem to guys who have bought a lot of these fancy GPUs and are spending a lot of time on it. So that's the short answer there. Unless you're one of them, don't worry about it. Just use it because they will have better economies of scale on that scaling problem than you will have. The other scaling problem you will have is around all this data that you need to make available to the model, right? So maybe you have, maybe you're lucky and you only have a couple of thousand internal documents that you want your to be able to speak to. So you don't have much of a scaling problem, right? But if you are doing web search, for example, and doing a RAG search on top of that, we all know a company that is doing that. Or if you want to make all kinds of financial information available in your RAG application, then you're dealing with lots of data, right? So you need to be able to convert all of that data to vectors and then store all of those vectors, index them. And if you want really good quality, you also need to index the text itself, and you have additional metadata that you want to filter by. You have found entities over your data and all of those things. So all of that is a lot of data. You can't fit it all in one node, and even if you did, you couldn't run all your queries in parallel on that single node. So we need a distributed system that can handle this scale for you by using many nodes, splitting the data into smaller pieces, and so on. So that's one piece of the puzzle. The second one is, as I mentioned, you want to deal with both vectors, text, and metadata, and you can't, because you need to scale it, you can't just put these different kinds of data in different systems and then join them together when you need them while you're evaluating a query, because you'll just run out of switch bandwidth sending data, these different kinds of data across the wire. So you need a system that can handle all of that data, different types of data together. And lastly, how do you find out which pieces of data that is relevant to problem at hand? If you want to do that really well, and doing it really well is important if you're doing RAG, more important than when you're dealing with humans, then you need machine learning, that is AI, also to do the ranking of all of that data, right? And those smaller machine learning models, much smaller than these large LLMs, need to run where the data is stored as well. So we need to distribute your machine learning to your data rather than trying to send the data somewhere to do inference, because that will just be too slow. So those are the general considerations that you have. Akash, I think may have some more practical.
I mean, it's working with you guys. That's been so much fun on the scaling problems. But let's talk about, if you want to build a billion document scale index, what does that look like? What are some of the issues you run into? What are some of the considerations that you might have? I'll start with the most basic one. There's some really good questions also coming, but I'll start with the most basic one. Just scaling the content itself, right? It's one thing, the old school ways of scaling textual based content, where you would build these inverted indices. They were pretty efficient. They were sparse storage, like you could store a lot of information. It wasn't too expensive, easy to retrieve. Scaling with vectors is an entirely different thing altogether. I forget the size of a single vector, but when you start scaling at a billion vector scale, retrieval becomes a big problem. Being able to sort and sift through a very large index that is billions of these vectors, it starts to become a problem. The other part of scaling, so there's the content scaling bits, and that's an entire topic just by itself, which is how do you store enough vectors not in memory to bankrupt yourselves. That's the biggest question, and I know it's something we've been working with Vespa for a long time, and they have a lot of very interesting takes on how to do it. We can go into that later. Outside of the content scale, the other part is scaling inference. right? So inference has to scale because every query that comes in, generally speaking, if you're building a production grade pipeline, you're not going to build a simple rank code. You're not going to be happy with cosine similarity. You're going to want to add, all different things into it. So it's like, do cosine similarity, do a TD-IDF search, do a hybrid, and get some results back. Now you're running a real-time system, which means real-time needs to have some notion of freshness. Freshness has notions of decay. How fresh is fresh? If you like publish something once every minute, then it decays really quickly. If you publish something once every quarter, the decays are really different. So you start thinking about all the feature sets that you need to create just for that at scale. And then the last one is, there are these notions of re-rankers or cross encoders that are like essentially GPUs that are running at the last bit that help you scale and saying, I found you from 1 billion documents, 300. Out of these 300, how do I again re-rank them all in real time, right? Because we're measuring latency here in 200 milliseconds or 1 second max of like latency. So scale is content problem, scale is an inference problem, and scale is also a distribution problem. What is the most optimum way to organize your content such that things that are retrieved heavily often they matter in terms of a latency framework? Things that are not don't actually matter, and you can probably federate your queries in a slightly different way. So scale is, I don't want to get into all of the details right now, but we have been tackling this in 3 different ways outside of the large language model scale, which is what kind of token per second can you support just by itself, because you're providing a lot of tokens every single time you run a search.
Yeah, great points, Arkash and John. And we got some great discussion going on in the chat here. So I'm going to pop a couple of questions that I see here up on the screen. So sorry to put you guys on the spot if these are too specific, but this one from Alan is he raises the issue of different processing efficiencies, and considering that and adding processing to the chunking and embedding process is one part of that. But then there's also the efficiency of retrieval and ensuring that you're retrieving relevant information. So any reaction to that from you guys?
Yeah, he's right. Those are 2 different efficiencies to consider, both from capacity scaling point of view, but also different dimensions on which you can measure if what you're doing is really good, right? So on the embedding side, if you're writing a lot of data, then you need a lot of embedding capacity. That's a third scaling dimension that you need to worry about, right? And you generally need GPU to run the models that are doing the embeddings as well. Similar to the LLMs, you can also use APIs for that kind of inference. But in this case, it's pretty feasible to run those models yourself, because the embedding models can generally be much smaller, and they also benefit more from being fine-tuned to your particular problem, right? So if you're doing that, then you have a third scaling problem that you need to worry about, getting GPUs for this. If your feeding is very bursty, what you want to have is to have some kind of auto-scaling enabled, right, where you can provision those GPUs to do your embedding only when you're feeding a lot of data, and then scale down, hopefully automatically, when you're not using them as much. On the retrieval side, there's both capacity and also the quality, right? And those are, of course, related. Generally, if you know what you're doing, you can always spend more CPU to get even better quality. So you sort of get a graph relationship between those 2 variables, right? And you need to pick a point where you're expending enough CPU to get good quality, but not spending outrageously much to get slightly even better quality. So the best way to do this is actually to plot that graph and pick a right point on the graph. So there's obviously a trade-off there. But on the relevancy side, this efficiency is really what we call relevancy, right? And on that side, it all starts with measurements. The first thing you need to ensure is that you can actually measure the quality of the data that you're retrieving. Otherwise, you're just flailing around in the darkness, and you don't know if your additional effort or additional CPU or your vector embeddings that you're paying a lot for are actually doing you any good. Right? So always start by measuring what you're doing and then improve gradually.
I think that's the like pretty much the main takeaway is before you even think about scaling, and I'll address a few of the follow-ups that are coming up right now. Having good eval sets is going to it's like if you don't have that, there's no point in actually doing any scaling work. Truly, there is no point in doing it. And I remember even before large language models, we had literally we would spend from 3 p.m. to 5 p.m. individually go and start tagging stuff for ourselves. So we had because we were building out our own golden sets. And a really good way to do it is have a beefy enough node, put about 100,000 documents inside it, keep it static, and then have a set of questions that you can then go evaluate. Large language models are very good for this right now, so it's very easy to scale with them. But what we had done was we had a static cluster and we had eval sets that were built, and every time we had a new ranking algorithm, we would deploy it against the static cluster. We would see the efficiency, we would track the NCDG scores, and then you're like, okay, this is not really disruptive. That works. I'm not saying it doesn't work. Eventually, what you're going to have to do is probably create a copy of your entire cluster, because everything that you assume works, when you roll it out and you see what users are trying to do, are completely different sets of results. So then it becomes basically something where quality and eval sets is a very key part of the scaling strategy. And you kind of have to have, your lab environment scaling sets, and then your real scaling sets where you're tracking this live and you're sampling continuously to make sure that people are getting relevant results. I will also address there's a lot of questions about chunking and embedding process and all of this. I agree that the world of embeddings move very fast. By the way, every time I think that we have a good embedding model, something new comes up, and we're like, oh, maybe we should go try that. So here's some battle tested ways that we went about this. One is you don't need a very beefy embedding model. Actually, you don't. You can train a good BERT model or a good sentence transformer model, and then you can train a student model that's 1/10 of the parameters, and you'll see a slight loss rate, but it won't be that much. So a big way that we scale, because we get about 40,000 documents a second. We get bursts like that at that speed. Your standard BERT inference things, yes, you can throw a lot of GPUs on it. Our recommended approach is to train a smaller model. You'll see a lot of uplift from there. Another thing with scale is what has come out literally just this year is moving to binary embeddings, or moving to Matryoshka, style embeddings. It's a little bit more GPU work, but it's actually much more efficient when you start retrieving the stuff at scale. So at our issues right now, even for us, and we'll speak about span at some point, I guess, but even without the Vespa span-like configuration, which is, a little bit in memory, most of it in desk, and just being smart about how you retrieve it. I think binary and Matryoshka embeddings are a completely different way of approaching the same problem. That's the embedding. On the chunking problem, it really depends on your data sets. We work with every large set of documents. We have some documents that are 300 pages long, some documents that are literally one line because it's a headline and it's a flash. And we have to support all those needs. So one of those things that we had done on the chunking side is we essentially built our own smart chunker. Every large document gets broken up into smaller chunks. We've decided to store each of those chunks as individual documents. I know that there are new techniques that are multi-doc retrievers and those types of things, but for the types of use cases we have, that a document can literally be a single line or a document can be 100 different chunks, we found a sweet spot, and it's somewhere between 0 and 512 tokens. I don't know the exact answer, but that is kind of the sweet spot that we ended up with at scale.
Yeah, really interesting points, guys. And the chat is definitely very active with some pretty technical questions. So we got another one here from David. I want to pop up here. He read that what works best is to use a high quality LLM for embeddings, and then a smaller LLM can be used effectively for inference. Is that what you guys have found, or is that different than what you're finding?
Yeah, I think that's sort of not what Akash was just saying,
Yeah, the
and
opposite
which
of
what
what
I
I'm
agree
saying,
to.
yeah.
Yeah, it's kind of the opposite in my experience as well. Embeddings aren't that precise anyway, right? You don't need a lot of intelligence for that. It's basically just sort of categorizing the information in the text, placing it in a vector space, right? While big LLMs, the frontier LLMs, can be really, really intelligent, right? And if you need that intelligence, you really need that big model. If you're doing a more narrow task like classifying text, or maybe even ranking text, depending on the domain, then you can use a smaller model. So you really need to think about how much intelligence do I need to solve the actual problem that I'm trying to solve. Don't kid yourself to think that just because the model is eloquent is also intelligence. For large language models, those are pretty separate, right? It can bullshit you all day eloquently, but there's no intelligence behind it.
Great insights there. And then Ibrahim is asking, is there anything wrong replying on cosine similarity alone?
It's going to fail you for sure. Like, do not rely on cosine similarity on your own. Truly, like I actually mean that. Like, it works really well for your tiny data sets. You got 10, even 10,000 documents. I can see that being effective. It really depends on the class of problems, right? If you want, like, if you're building a new search engine like us, it's not really the embedding that matters more. It's the freshness, it's the metadata inside it, it's the keyword with the hybrids. And then the embedding adds a lot of value in potentially finding you good candidates. And to John's point, it's actually a critical thing that I think everybody should just know, that the embeddings actually don't matter that much at the largest of large scales. It's a feature as part of a much larger pipeline. And where you start to get a lot of bang for buck actually is on the cross encoders, because like it really helps. That last re-ranking bit is actually a very, very effective way of saying, but this is my query, these are a bunch of I think related queries, which one actually is answering that question? And once again, the eval sets are like your holy grail, because this is a very long, very complex pipeline. Ultimately, you have to actually see an end-to-end pipeline, not the individual components.
Yeah, I completely agree. And if you look at benchmarks from academia, they pretty unanimously show that relying on cosine similarity will not give you good relevance, right? So if you only want to do one simple thing, don't use vectors at all. Use traditional text search from the 70s with BM25. That will give you better quality and it's a lot cheaper and simpler as well. Right? But as Akash said, you get the best quality by combining multiple techniques in the same query and the same ranking, right? Even something as simple as standard hybrid search, where you retrieve both by vector similarity but also by old school text search, and then get results from both, and then combine relevancy signals from both sides into your final relevancy. It gives you much better quality than just cosine similarity or BM25 on the text side alone. And you can easily see the intuition behind this, right? If you are doing only text search, your retrieval will be very precise, right? If you are searching for some words, you will only retrieve documents that have exactly those words. Sometimes that's good, right? Is really what you want. If you're searching for whatever product you have on ASIL 25B in your warehouse, you actually want only that ISIL, right? And if you're searching for some person that works in your company, you only want that particular person and so on ad infinitum, right? But sometimes it's bad because what you're searching for is more like a concept, and there are other ways to express the same concept, right? And that's where vectors really shine. So what you want in general is to combine the best of both worlds, right? And hybrid, which really gives you that.
I mean, there's some great questions coming here. So we can just say,
Yeah,
seems like the embeddings is the really contentious topic, or I mean, like we can answer a lot of these questions. We can just go with the Colbert answer because I am a huge fan of Colbert, by the way. We've done a lot of experimentation here internally on it. I think it's really the first question we should ask ourselves is Vespa's implementation of Colbert. I don't mean to toot your horn here, John, but I liked your approach towards it. Is that Colbert is one of the most inefficient ways, by the way. It's like token level embeddings. You're storing a crap ton of embeddings. It's very compute heavy at the indexing time. So if you have any issues where this document came into my pipe and I have a Kafka sync somewhere, and then I got to get this inside the index really quick, Colbert is really going to stress that system massively because of the amount of embeddings that it has to generate per document. FYI, that's kind of why we've paused on it right now, because we need to figure out the indexing part. But if you have a smaller data set, Colbert with late interaction, the way like Vespa has done it, which is basically doing it at the end. Like finally, it's like being able to deploy Colbert and run the compute or the calculation, the per token calculation in the last set of documents that you received is probably the most efficient way I've seen it being implemented. I think Colbert and like sparse models like this that can give you the token level attention is a phenomenal technique. It's just like it's such a big drastic shift and it's such a big architectural change for us that we are getting enough output out of using like buy encoders today that we're sitting quiet and we're testing more about how easily it is for us to integrate a Colbert like system into this pipeline, because it is fundamentally a lot of different changes that have to be made. I don't know, John, if you want to talk about the whole, like, systems that have already grown up in the buy encoder world to move to a later interaction world. What are some of the complications that come with something like that?
Yeah, I can talk a bit about that. So I agree with Shivi here that Colbert is, and especially version 2 is a great retrieval model, right? We were very excited when that came out, and we could support it on Vespa just by expressing it in our tensor language. So we didn't actually make any features to support Colbert. You can just express all of these models on Vespa as they are in various ways. So no work on our side on that. But the problem with Colbert that Akash touched upon is you get lots and lots of vectors, right? So if you already have a big data set, then it will be extremely expensive. So where it really shines in most use cases that we see around it is when you combine it with binary vectors, first thing, and secondly, Matryoshka style vectors where you use a model that trains a vector where the first numbers are the most important and then the importance of numbers trail off, because then you can make the vector really short, right? And if you use those techniques, you can index these tokens with vectors that are just a couple of bytes. And then you start getting something that is economic at scale. So that's where a lot of the excitement is at this point, I think. And by the way, if you haven't looked into it, look at stuff like Colpali as well, where you move away from text entirely. If you have more visual documents like many PDF reports and stuff like that, right? Recently, there emerged a completely separate technique where you don't do text embeddings or text indexing at all. You just digest the documents as images and cut the images into patches, similar to chunking and then create one vector per each of these patches, and you index those patches similar to Colpoly and retrieve them similar to Colbert and retrieve them in the same way with maximum similarity. And that really gives you great results if you have a good visual model that can do this. So that's a technique that we are very excited about these days.
Yeah, excellent points. And John, there was a follow-up to that in the chat. Is it possible to use Colpoly text and images with another embedding in the same instance as Vespa?
Yes.
Great.
Short answer.
So we got another question
about that. But sorry, go ahead, Brian. Yes.
No, we talked about testing the accuracy of responses, and Elias wanted to know how that works at scale. While there are data sets for training, now you're dealing with new and very company-specific data. So how do you ensure the LLM is performing well for your data specifically? What do you guys think of that one?
Do you want to do that one, Akash?
Yeah. Honestly, you have to just build. So the easiest thing that we've done is really just create search boxes with really bad results, and just give it to people to start asking questions. And then, like, the minute you start asking questions, then you start seeing that the types of things that people are asking from your own data. Then you build that eval set. And oftentimes, I mean, like, where we ended up actually is we fine-tuned the sentence transformer models itself. So before, like, we're not using an open source off-the-shelf model. It didn't work for our specific domain. So what we needed to do is take like a sentence transformer, fine-tune it on sentence pairs, and then you can use large language models to create all of these, like, like negative samples and stuff, and then train it more on your specific style of information with your specific size of however you chunk, because then you're essentially creating something that understands your language a lot better, and you're teaching it what is similar and not similar in your domain. Outside of that, the only thing that would save you is the metadata that you attach to every single document. And especially when it comes to like company specific information, it really is helpful to have company specific metadata indexed somewhere inside the schema, so then you can query it and be smarter when you query it. Because you can do a lot of stuff where, we store, for example, any of the entities that we detect. They're stored in arrays and structs and tensors and a whole bunch of different places inside a single document. And when somebody asks a question, right, like, what is the latest news about Apple? One of the things that we do is at inference time, what is the latest news about Apple? We're detecting Apple itself and saying, oh, we know Apple, this is a company. Let's attach that into the query, because it'll help the query be a lot better. I'm already telling it that I know something about the user's intent. So there's a lot of stuff that you'll end up starting to do that's more intent driven, which is identifying the right intent, being able to parse that intent into a series of like search parameters. So you're not always depending on something that doesn't really understand who you are, what your domain is, what type of documents you have, and how you want to go retrieve it. And that's kind of where I've seen a lot of these POCs with clients fail, is everybody assumes you can use something off the shelf because it's been trained on enough information or it's seen enough, but it's not actually trained to know what's similar to you and to your specific needs. And that's something that it's a small thing, but that with like contextual, like chunking, we've been doing contextual chunking for so long that we always added the title into every chunk, so it had some information about the original document. Yes, now we will run small language models that are fine-tuned on just adding a little piece. Or Gina actually came out with a really good paper on late chunking, which is, you create an embedding on the full document, and then every chunk is a forward pass of the original embedding, so it kind of retains some document level embedding information. It's just like the space is moving so fast that it's sometimes just really hard to keep up.
Yeah, great points, Akash. And my next question kind of ties into David's question here in the chat. So David's asking, instinctively matching against images, computer vision model is going to be much more costly than text. Is this the case in practice? Is performance affected? And then I want to to also take that sort of one level higher of just what are some best practices? I mean, in terms of controlling for cost, in terms of performance, how do organizations figure out, what are some guiding best practices they should use when implementing scalable AI systems with RAG?
Yeah, the first part is easy to answer. The other one is a really big topic that we can spend hours on, right? But yes, the computer vision models using that is more expensive than simple retrieval models where you just index all the text or you create a bunch of vector embeddings, right? But if you compare to something that gives you comparable quality like Colbert, then at least with the new work we have done around combining it with binary vectors and so on, it's not more expensive and the quality is higher. Even only on texts, actually, we get higher quality with this method, which is kind of baffling to me. So it depends on what your baseline is. Do we really want really good quality so that you're considering something like Colbert? Then it makes sense to consider this instead. It both simplifies your pipeline, right? Because you don't need to do all this text pre-processing, extracting text from PDF, cleaning it up, chunking it, and so on. And it gives you typically better quality because the model can see all the information that is there originally. There's a reason we are putting in figures and graphs and pie charts and whatnot in our documents, right? It's to represent information in a more accessible form, and that benefits these models as well. On your larger question, it's a really big question. Really, it comes down to what's the actual business value of spending more resources and therefore money on some problem, right? Yeah, it's a really big question to ask. Akarsh, do you have the answer?
No, it's this is a 2-year-long conversation to go have right now.
Well, we've talked a bit about just sort of how fast this space is moving and how it is impacting everything, and what the models that you have one day, you might have different models or techniques a different day as a result of how fast we're moving. So what are you guys' predictions as far as the advancements that we're going to see in AI and infrastructure that's going to shape the future of these technologies over the next few years? What do you think things are headed as far as trend lines?
Yeah, I think it will continue on the same path with the new thing that we didn't consider until the last half year is this visual models. So on exactly what we're doing, I don't think we'll see a big revolution. It's more continuation of the current practices with that addition. One thing that is going to change that I think will be really important though is you will get a lot more additional leverage, meaning ultimately intelligence, out of investing more compute power on inference versus training, all things considered. That's what OpenAI was able to show with their O1 model, right? That if they for the first time showed that you actually could do chain of thought that actually worked, that you could spend 2 minutes thinking about the problem and then come up with a better answer, right? That isn't there yet for enterprises, right? And enterprise data, but we're going to get there. And what will happen then is that when somebody needs a problem solved or a question answered or something, it doesn't translate to a single query in your data, right? It will translate to many, many queries, maybe thousands of queries as the model is exploring the space of possible answers, going down paths to explore something further if it's relevant to the answer and so on. So then we will have another scaling problem, not just scaling to fit all your data, but also scaling to be able to handle all this, the torrent of queries that will come from the model to solve one single problem.
Yeah, on my side, outside of just what John just said, but truly is like reasoning just changes the game in a lot of ways. but there's so many parts to this pipeline, right? Like, if reasoning is so good, should we just send like, 1 million retrieve chunks to an agent and said, just go reason through these junky things that I have, and it's good enough. I don't need anything else in my pipeline. I can just give it to it if you don't like worry about latency. But if you do worry about latency, then reasoning becomes a problem. If you do worry about what we're seeing in real world today is that when you actually look at the class of problems that users are trying to solve and their expectation from what the agent is, or like what your interface is supposed to do, the expectation is, I ask you a question, figure it out, right? Like, that's really the expectation right now. And I blame ChatGPT and other types of inferences like this because they kind of created that new thing or the new expectation from users. Where I'm seeing there being a lot of effort, even we're spending a lot of effort on this, is you can start divvying up your world into classes of problems. Each class of problems can have a router. The router, you have a parent router that is routing your queries to smaller tool sets, but those tool sets itself are their own workflows. So it's a RAG agent with a reference agent and everything wrapped up in a tool API call that gives you a response with some kind of output. That's kind of where we're seeing, like, if 90% of your problems are what is the latest price for something else, let's solve that problem. You don't actually need to go solve everything with RAG. And that's kind of where we're seeing that as these systems evolve and they start becoming bigger and smarter, it's actually creating an orchestration layer, having very clearly defined query routes, having something that is your catch-all, be-all, end-all, where everything is going to go. But then you're building all this other stuff to account for your queries. And truly, this is not just a technical problem. This is a systems design problem. Like, just being able, like, I see this a lot where somebody just thinks like throwing a vector database on something will magically solve all their needs. And then most of those projects I've seen fail in real time when you actually roll it out, because the obsession is not with the user queries and what the user is trying to achieve out of the system. And then you work backwards from there.
Yeah, I guess, how do you ensure that you are aligned with what the user is asking? What do you think is the best way to understand that, and like what kind of teams do you need to build to be able to get the answer to that? How do you work together collaboratively in a large enterprise, for instance, to figure out how the system's actually going to work to make sure that it is successful?
Eval sets. You better have a very good, and I'm serious, like, it sounds so trivial because anybody can come up with an eval set. I can promise you, in real production systems, eval sets become the most like crazy obsession of everybody else, because it's not really about, these pipelines will get more complicated, right? And ultimately the user sees an input and an output. That's your only benchmark, the input and the output, leaving aside the pipeline. So my suggestion is, like, for most people that are on this journey, if you can't answer the question of what your user needs to get out of it, then you're probably not, like, by going the route of embeddings or something, it's probably premature. Don't do that right now. Go figure out first, like, the class of queries that users are trying to solve for, and then work backwards and then say, how do I incorporate it, these types of powerful systems for it? And I'll give you an example, right? John brought up like the Copilot. Obviously, we work with a lot of PDF stuff. We work with financial firms. They have a lot of broker research. It literally is the definition of Copilot. The question we have is, it's one thing to retrieve and give an answer back to a client, but it's very different if a client comes in and says, okay, let's look at that table, and I need to ask you 3 more questions with that table. Because at some point, I gotta have to have that table parsed, send it to a like large language model, and actually get it to answer a question. And that's kind of why with like Copilot, it is probably one of the best retrievers we've seen. We're probably gonna head in that direction, whether we like it or not. But it's not the be all end all, because you really have to look at the class of questions that people are asking. And then you may realize you kind of do need the OCR to parse out the tables. You don't need it for images anymore, and then you have to make a decision where, like, what do you want to do, what do you not want to do, and just throwing a table by itself is not enough. It has to be a table in a markdown format that is accessible to a large language model to do it. Do you do it before, or do you do it at compute time? And these are all questions that we solve, live, but these are the things that actually happen in these real-time systems at scale.
Yeah, great points and examples there. So we're running towards the end of our time here, but I want to jump to our lightning round and ask you to share a key takeaway on optimizing AI systems for scalability and performance. So if you guys had to wrap it all up in a bow and give folks one or two takeaways, what would they be? Let's start with you, John.
Okay, I'm going to steal Akarash's points so that I can hear what else he has to say. Start with evals, start really simple. Not with vectors, start with BM25 if you're doing something with text at all. And then only add stuff as you can prove with your evals that it actually helps you. I think people are way too eager in general to add complexity prematurely because it's cool and interesting. And it is, right? But always prove that you're adding value.
Great point. Akash, what do you think?
I guess a big thing would be worry about your indexing pipeline, because it will make or break you. It matters more for us because we are a real-time system, and those indexing pipelines are pretty beefy, and they've been rewritten a few times with a lot of different inference techniques for scale. But you will be surprised at how important the indexing is, how important your chunking strategy is, how important, like, leaving aside all the other stuff. So if you can do better indexing, better chunking, BM25, and a good eval set, I would just start there and just iterate on that. And then you add a feature and you do like reciprocal rank fusion with like embeddings. Embeddings works really well if if your users are typing in a product name, you don't really need embeddings, truly. But if your users are naturally tuned to ask long questions, then embeddings actually are really good. Then like that's where we see the most bang for buck, when it's like not 1 or 2 words, it's 4 or 5 words. There's semantic information encoded in the sequence of how you ask the question. Having that run against the vector search, that's where these things really shine, and you see a big lift.
Yeah, excellent points, and thank you guys. This was an excellent technical discussion. I think one of the most active chats we've had in a very long time. You guys did a great job answering all of these very specific questions. So very much enjoyed the discussion and the learnings. And if you guys missed any of the webinar or want to rewatch anything, the recording will be available just a few minutes afterwards. If you just refresh this page. And want to say a special thank you again to our partners at Vespa for making this webinar possible. So thank you all again, and we'll see you next time. Thanks.
Thanks, guys.
Thank you.
This was fun.
Yeah, appreciate it.